Today would be the boiler and the cooling water, chemicals and the corrosions. And on Thursday would be how to do the testing. So water systems on board we are concerned of in these training is boiler, engine, evaporator, portable water and spa and pool. This is just giving an overall view of how complex the water system is on board the vessel. But boiler water corrosion. So boilers. We have two basic types of boilers. With here is a shell boiler, or sometimes called a horizontal boiler. It's for the lower pressure sides. A lot of car carriers will carry this type of boiler, or ferries, where they don't need much steam and they don't need a high pressure. The more common one on board the vessels is a vertical tube for the larger vessels. The more you're talking 8 to 32 bar boilers, a lot more water, a lot more pressure. But I'm not going too much into the boilers. It was just to touch on that subject. I've flicked down here so you can see it all. When you're talking about boilers, people only talk about water. They want to stop the water being corrosive. But in a boiler operation, you've got to actually understand how water works with the steam and how often you need to change that water. This is a basic calculation how to change the water. You should always be looking at something called cycles. A cycle, when you want to keep the water in a reasonable quality, you're looking at 20 cycles, which means you times the tonnage of the boiler, which is 10 ton of water a day. If you blow down twice a day at, say, 250 kilos, you equal half a ton of blowdowns a day of water. So you then divide 10 by half a ton equals 20 cycles. It's a simple calculation. If you cycle more than 20, you're actually keeping more of the impurities in the boiler, which means you're actually doing a lot. You're sandpapering the metal, and you can actually reduce the boiler metal surface. If you blow down too often, you are wasting water and chemicals. So it's a fine balance how you should be looking after this water. Things we should be looking at also in boiler is scale deposits, iron oxide depositions, condensate line corrosion and pitting. Unless if you don't do that, you get things like this. This lovely boiler on the top left hand side blew out of the ship on the top right hand side. As you can see, it's a vertical tube boiler because of all the tubes going upwards. Literally, it blew out of the funnel and it landed on the back deck. And that was all down to corrosion. That particular boiler wasn't actually protected by any chemicals to my knowledge. Here is a typical report from DNV when they've done a boiler surveys. They see a lot of problems, mainly due to the water, but also the excuse me, mainly due to the water being not protected correctly. There's ways of protecting it. One is to keep the hot water hot to stop the oxygen getting into the boiler through keeping the oxygen biomechanically heated. Then you've got the chemicals which can kill the rest of the oxygen, and other chemicals to condition the water. But also, which a problem they don't talk about too often, is the point number 4 down here, soot fires. A lot of people forget the soot side of the boiler system is actually part of the boiler system. Very frequently, yeah, ships have soot fires, but it's not recorded or it's not advertised well. So you should always keep, especially on the exhaust gas boilers, keep the soot side clean, because when the fire starts, it's like a welding torch cutting through metal. Here we've got some examples of metal surface. The top right hand one is got oxygen corrosion, as you can see by the rusting. The one on the right hand side though, it's got a nice coating on there, nice evenly. Anybody know the names of that coating? Any guesses?
No idea.
Do you mean the metal coating or the chemical product?
I'm meaning when you've got the rusting, it's through poor oxygen. On the right hand side, the one with black colour, that's actually got a coating done by chemicals, but it's actually it's not a chemical coating. It's just a how can you say it? It's a magnetite layer. If you ever open a boiler and it's protected correctly, when you see it, it should show a black surface with either a shiny black surface, or if you put your hand on it, your hand will get covered in black fine particles like a dust. That's called magnetite, and that is actually what you should have. That is putting a metal surface, or as we call it, an eggshell around the boiler to stop the water touching the metal. That's done by chemical control over the oxygen. So again, if you don't have the, like I said, the bottom right hand one, again, that's got magnetite on it. You can see the clean, even surface like an eggshell. Otherwise, you get oxygen pitting like the top one. So most common corrosions by oxygen is because of idle boilers, or especially this particular time, we've got a load of vessels out there in cold layups. Cold layup is when the vessel is in a dormant state and the boiler is either cold with water in it, or left small pressure, say 2 bar, and just ticking over. If they don't maintain the chemicals, you get accelerated corrosion. If you're going to leave an engine or boiler system unprotected for a long time, as in a lot of these vessels which are just anchored around the world, they should either empty the boiler or fill it 100% up with chemical and water. Have you ever heard of wet layups and dry layups before?
Yeah.
The big difference is a dry layup, you just totally empty the boiler, the water systems. But that is if you are going to have a vessel off hire or rotation for 6+ months. It takes a lot of money and a lot of man hours to bring a vessel back to life again once it's in a dry layup state. A wet layup state is where they can reactivate it within, say, 1 or 2 months. So a lot of the vessels, especially anchored in the Norwegian fjords, are wet laid up. because they're hoping in the next couple of months it can be used again. But a lot of places like in Asia, they've got vessels stacked up in the hundreds. Most of them will be dry laid up with minimum crew, as in maybe a riding crew going between vessels. Let's hope you don't work on vessels like that. So when we're talking about oxygen in water, and what I mentioned a couple of minutes ago, engineering the oxygen out of the water, this graph shows you, if you look at the pink dots, that is water at atmospheric pressure, the pressure we're in now. So if we need to get rid of all the oxygen out of the water, we will need to bring the boiler up to, correction, we'll have to bring the hot water up to 100 degrees before putting it into the boiler. But quite often hot wells are under at least 1 bar after the feed pump, 1 to 18 bars quite often. So we can actually reduce the temperature to around about 80 degrees to be able to kill the oxygen, and only use chemicals for the last couple of percentages or ppm. Other contaminants in the boiler: oil and scale. There's a couple of others, but these are the biggest problems we have, the boilers you'll be using in your lifespan, unless you're going to go on to a high pressure boiler vessel, which is super tankers and that side. When you've got scale or oil deposits, one, it's causing problems with the metal surface. You're going to get blockages, you're going to get inconsistency in heated surfaces and superheated surfaces. But one of the biggest problems is actually the furnace temperature compared to what it should be. The next one will explain a little bit better. If you've got the metal, which is S2, you normally know in your furnace temperature to get the hot well, correction, the boiler up to 170 degrees. But the sediment, be it oil or scale or any other deposits, will affect that temperature to the point of, if you've got no sediment on this particular boiler, to get your temperature up to the correct, the boiler to the correct water temperature, you would normally have the furnace at 256 degrees. If you, on the other hand, have oil in the boiler, you would have to increase the furnace temperature up to 633 degrees to get the same water temperature. So it's important to make sure you don't have oil in the boiler, scale, carbon, or silica. But oil is the worst one. Silica is more prominent if you have a high pressure boiler, not low pressure. Does that sound logical?
Yeah.
Yep. Okay. Contamination of the boiler, like the screen a couple of minutes ago was. If you the most common 2 types of corrosion is actually scale. That's normally coming from seawater ingress through the condensate system, or oil through the heating coils of your fuel tanks. But if you actually put strange metals like copper in the boilers, which some vessels have, some of the older vessels have, or in fact, if you put too much chemicals, certain oxygen scavenging chemicals, you can actually make ammonia coming back from your steam lines. Again, that's highly corrosive and extra poisonous. Scales. This is typical photographs of scale buildups in your steam pipes. As you can see on the top one, you're going to have to heat that steam pipe a lot more to heat the water to get through the scale. I actually got this slide from a colleague of mine yesterday, and I found it's giving me the wrong pictures. The bottom right-hand picture, that's scale from the sewage pipe. So if you're on the ship, if you flush in the toilets and you don't descale it, your pipe will look like that. You can actually see the shit deposits built in with the scale. So my apologies for that picture. But it does actually show how scale can build up and how easy it could block up your, not only the boiler side, but actually the sewage treatment side according to that. This is a lovely picture of a hot well. Hot wells should be as clean as a boiler. And one of the big problems we have is a hot well, our boiler system should be a dynamic sealed system. These pictures were taken by myself on board a vessel because when they was running the boiler, steam was, I'm just trying to find the right word for this, was actually steaming, and you couldn't get close to the hot well because of the quantity of steam around the hot well. So that was one very unproductive of using other fuel to actually produce the steam for the boiler, but it was actually really bad for the system because they was actually putting chemicals directly into the hot well to go into the boiler, and half the chemicals was actually evaporating before it could actually do its job in the boiler. So on this particular case, there was wasting, one, the fuel, and two, all the chemicals. But if you look at the bottom picture, the one with the brown rust, you can actually see oil on the surface as well. So they weren't actually cleaning the water properly either. But hot well is a really important part of the boiler system, and it's always forgotten. But you've got to remember the water for the boiler system is coming through the hot well. So if you don't maintain your hot well clean and to a good condition, your boiler is never going to be running well. But a basic principle of chemistry, what happens if you put any metal in water, you get corrosion. You put any salt water through an evaporator or through a heating plate, you're going to get scale. So whatever you do in the boiler, something is going to be a problem. So that's why we treat the water with chemicals or with pre-treatment through the hot well system. When we come to the chemistries into the boilers, we are trying to do multiple things. As it says here, we want to dissolve the gases, prominently oxygen, which is the most corrosive of the gases from fresh water. So we want to dissolve the oxygen, one, to stop the oxygen pitting in the boiler, but two, if oxygen gets carried over into your steam lines, that becomes very acidic and corrosive onto your steam heating coils for your fuel, which will then bring oil into your boiler if the corrosion gets through the metal. So we're working on that part to kill the oxygen, but we're also trying to reduce the hardness salts and pollutants like oils, acids, muds. So that's why you need multiple chemicals. There's not one chemical can do everything. I've just touched on this, so I won't carry on that one. CO2 and oxygen are the biggest killers of boilers. And I've mentioned oxygen a few times because it is very important. So we're looking at the problems. The salts is one of the big things. So we would actually always recommend good water quality. In boilers especially, but cooling water also. Always use technical water or evaporated water. Shore water, we do not know the purity of that water. There's a lot. Shore water can carry a lot more hardness salts, a lot of pollutants, and it is not good in a boiler at all. We've got chemicals which can assist if you have to use shore water. It's not part of our normal programs, but we'd have to put a chemical with higher phosphates and polymers in there. So the more impurities, the more other chemicals we'd have to put in to condition that water. So the best for you would be to use technical water all the time in the boiler system and do plenty of blowdowns. If you're low pH in the boiler, you put some more alkaline boiler chem in there. If you've got too high alkalinity, you increase the top blowdowns. But as I mentioned earlier, where it says there's a low condensate pH, that's because it's carried CO2 or oxygen from the boiler. It's very aggressive, so we'd have to use something called a neutralizing amines, which is a very volatile chemical which goes with the steam. All other chemicals we give you will not carry over to the steam lines. I've explained this earlier about the oxygen. So here's a few of the problems I see quite often on boilers. The common problems I see in boilers: temperature of the hot well too low. The reason I'm saying that is we recommend the temperature of the hot well no lower than 80 degrees. You'd find most systems cannot go above 92 degrees because of cavitation in your feed pumps. But anything less than 80 degrees, you will have to put 7 to 10 times more oxygen per degree below 80 degrees to kill the oxygen. So you have to put in instead of putting, say, half a litre in a day on most systems, you might have to put 10 litres a day if it's below 80 degrees. So you are wasting a lot of money on chemicals. Chemicals you shouldn't need to be using. So it's important to keep the hot well temperature 80 plus degrees. And the other one is return condensate line and makeup line are fitted above water level. It should always be returning back into the hot well below water level, because if it's above water level, it's actually the water is hungry for oxygen. It's been deprived of oxygen in the hot well, in the boiler system, and in the steam lines. So if you are bringing water back into the hot well, as in an open tap situation, it's going to soak up oxygen straight away from that. And that is defeating all the chemicals you're putting in there. So you want to have the system as low as oxygen as possible. So the return line has to be below water level. Hot well covers open. It became, like I said earlier with the steam, it actually is absorbing oxygens and also evaporating chemicals. So it's actually doing a lot of damage. Temperature of the hot well. We want to keep it again as high as 90 degrees, but consider the feed pump. The temperature of the feed pump and the cavitation. Now, with regarding chemicals of the boiler, we have multiple chemicals, but to simplify it, oxygen scavengers remove oxygen from the water or puts a barrier on the surfaces to stop the oxygen doing damage. Most common scavengers are taking the oxygen out of water. But if you want a food safe, if you're using steam in a food environment, you have to use a barrier rather than an oxygen depleter. Because the oxygen depleters, or the scavengers, are poisonous to food. So depending on your use of the steam after the boiler, say you might be working on a fish factory vessel. They use steam part of the processing in the fish industry. So you can't have chemicals which are poisonous in your boiler system. But majority of you will be on vessels where the steam, you're not bothered about the steam. Alkalinities to condition your boiler. Then we have certain chemicals to condition your boiler with to bring their pH into a neutral or alkaline positive, so there's no corrosion going on there. Scale inhibitors and dispersants. Dispersants are where they can actually assist your blowdowns in taking more heavy particles out. And neutralizing amines. These are basically the 4 different jobs of chemicals on board for the boiler treatment. To do this, we have multiple different, especially in Wilhelmsen, we've got multiple different options for you. But we decide, well, we've always broken them into 2 different scenarios. One is a combined product. There's not one chemical which can do everything, but we have reduced it to 2 chemicals. One which will cover the pH, phosphates, and the scale inhibitors and deposits, and one with the oxygen. And it works very well because splitting the neutralizing amines for the condensate between both of them, it becomes a very good combination. And that's our most popular range at this moment. But if you've got a high pressure boiler or a more delicate boiler, we have a coordinated treatment program which covers all of the problems with individual chemicals. As in this, a combined treatment would have auto treat, which covers your alkalinity, your pH, your phosphate for conditioning the heat transfers, and coagulants for taking away all the dirt and the sediments. Then the oxygen scavenger will have something called a DHA, which will neutralize the oxygen. Or we can go by the coordinated treatment program, which itself has alkaline chemicals, condensate chemicals, oxygen scavenger chemicals, hardness, and boiler coagulant. So there you'll be dosing 5 different chemicals. On hot water, on high pressure systems, you have to go that direction. I mean, anything above 32 bars. But some vessels like to do it above 16 bars, mainly the tankers. I take it most of you have been at sea, have used the auto treat and oxygen scavenger chemicals because that's our most popular range, especially for the car carriers and the trade coming from Europe. There's not many high pressure boilers out there other than the ones managed by Asia companies at the moment or BP from Britain, UK. Here is some of the parameters we should be looking at in all our chemicals or the boilers. This is a typical high pressure boiler testing program. I said you would normally be looking at the less than 18 bar scenario, but it can get very complicated. When you're doing your testing of the boilers, have you going to rephrase it? When you've taken water samples for your boiler, have you ever seen these scenarios? I see them quite often.
Yeah, the middle one.
Yeah, I think we had a similar as the middle one.
These are very, very common, and I'm sorry to say that they are very, very bad practice. The middle one is actually the better one out of the three, but if you can see the steam coming out of the cup, it's not actually cooling the water sample.
We had it looked like the middle one, but we got cold water out from it. We had cooling water inside.
That's good because the idea is you're cooling a sample without bringing contaminants into the sample. So if you're producing steam from that water, when you put it to one side to cool down, you are then taking oxygen from the environment into that water, which means all your tests will be a waste of time. So if you've cooled it down like you've said, using something like this, a sample cooler,
Exactly.
you will have a lot better water sample, which will give you the correct results of your water in the boiler. If it's coming like the steam is coming out there, that water sample is a waste of time. It's going to give you the wrong results. And the one thing I'm saying wrong results is the water in the boiler might be perfect, but by the time the steam is cooled down, the water sample is not representative of what's in the boiler. So you might end up putting too much chemical in because that sample says you need more chemical. So it's important when you're doing the test, you've got a representative of the water sample in the boiler. And these three pictures will give you really bad samples. So I'm glad that you've used the correct version, as in that type. I would actually say about 30% of the vessels I go on have something similar to these. So it's more common than what you would believe. And these are just the quick examples why it's important. But if you've used them sample coolers, we don't need to chew on this. The reason I put it in here is because it's such a very important thing that you should be getting the correct water sample. And the simple thing is, if you can hold the sample in your hand for 1 minute, it's cold enough to do the testing. The official BS temperature is 25 degrees, but as long as you can hold it in your hand, it's round about 25 degrees.
I have a question there when taking a water sample.
Yep. Okay.
Besides cooling it, you want a continuous flow. Is that correct?
Correct. What you need to do is depending on the distance your sample cooler is from your boiler, some vessels can be about 40, 50 meters away. So first you want to make sure your sample is of the boiler water, not old sample from the sample line. So you want to run it for a couple of minutes to make sure that you've actually got a representative of the boiler sample. so it's coming out as steam basically. Then you reduce the temperature so that you can actually have a steady stream, not a fast stream, but a steady stream, so you can actually take a sample. The slower the stream, the better it is, because it's going to, one, cool the water better, but two, bring in less oxygen. So if you've got it on full, if you've got the sample line up and full, it's going to be harder to cool it down, and the water is going to be, as it's moving so quickly, it's going to be trying to take as much oxygen as it can at that speed. So if you can take a slow, steady stream, leave it for a couple of minutes to make sure that it's actually from the boiler, that is the best water you can get. As soon as you fill the bottle, fill it to the top, then put the stopper in it so that there's no oxygen layer left in the bottle, so that you can take it straight over to take samples. It's important that you don't have any oxygen contamination. So the treatment, as I said, we have got plenty of chemicals to choose from. The reds at the bottom we are slowly phasing out, but there's a lot of chemicals there to choose from in your boiler system. The most two common ones you will be using most probably is auto treat, which covers alkaline, the antifoam, the phosphate, for the balancing of the water condition, the polymers, and the blended amines to assist in the oxygen correction in the neutralizing the pH in the condensate. That is all in that one chemical. Then the oxygen scavenger, which we use in DHA, and it also carries some amines. Them two chemicals together will cover, put it one way, that's about 70% of our boiler chemicals we sell today. Even though we have such a combination here, Oxygen Scavenger Plus and Auto Treat covers about 70% of the ships we deal with today. So it's a very, very well used program. Resulting in nice clean metal. This was a boiler survey one of my colleagues did in Germany early on this year, and it was a DNV 3-year service. As you can see, there's no pitting, there's no damage at all after 3 years of service. But when it comes to testing of the boilers, this is a representative of a company in Norway. All of the vessels are the same. They're the same boiler systems, the same vessel types. But this is a 3-year boiler program they used on every vessel. Not two vessels are using the same amount of chemicals over the 3-year period. Bear in mind, the vessels are doing the same trading patterns, so they should actually be similar, but this is all down to how they do the testing on board the vessels. How they do the testing and how much blowdowns they do. So without proper training, you could have vessels using too much chemicals, as the top one in the middle, the green one. They was blowing down and blowing down and blowing down, and they just overused the chemicals. So this is just an overview of how inconsistent the engineers are doing the testing and the blowdowns. That's one fleet of all identical vessels. So these are the things I normally ask questions, but you can ask a question yourself. How often is a boiler water treatment added? Where is it added? Is there any dosing equipment in place? And the problems which you can get quite often is scale building up? Is there any corrosion? And other questions. These are all added to that inconsistency. So you should actually be blowing down the boilers about twice a day, but only a small blowdown. And even the technique of blowing down a boiler can make a difference. If you open the tap 100% quickly, you will get a very high water flow, but you will not get a lot of the sediment out to the bottom of the boiler. Opening the blowdown valve slowly will get more sediment, like on a beach. You got the water taking away the sand. Compared to if you open it very quickly, it's like a cliff. It's taking no sediment away. So the techniques of blowing down can make a big difference. Of one, how much water you waste or throw away, and how much dirt it takes away with it. Adding the chemicals, where is the chemicals being added? If you had it directly into the hot well and you've got a open hot well, a lot of that chemical would be evaporated off. Also, some of them chemicals could be actually cancerous. So you are getting a face full of evaporated, possibly cancer forming chemicals. So adding the chemicals via a dosing pump, or by adding the chemicals below water level in the hot well, would mean that chemical you're putting in is safer for you, but also being used better in the boiler system. If the dosing pump's available, that's even better. But a lot of vessels still use the jug to put in the chemicals into the hot well. So like I said, then we go down into the problems. Is a scale building up? If so, then maybe the chemicals are not doing its job. Or you're putting too much pressure on the boiler, which could actually result in an explosion. Is a occurring? You're not putting enough chemical in, and you could actually have leakages of either salt water into your boiler, oil into your boiler, or you could actually be putting leakages in the furnace, which actually could bring soot or other problems from the furnace. So these all add to them inconsistencies. So it's very important for the person who's doing the tests and doing the blowdown to do the job as best they can, and not just do it as a standard routine. Cooling water corrosion. This is in itself simpler but more complex because the water is actually sitting there for longer periods. Generally, we break it down to two systems, here high temperature and low temperature, but if you go on a cruise vessel, you could have up to one of the cruise vessels I visited last year, they had 22 cooling water systems on board, ranging from high temperature, low temperature, main engine to actually air conditioned loops and a lot of others. So it can be more complex than what you're even thinking about. There's a lot more tolerances needed in the cooling water system compared to a boiler system because the boiler is normally closed looped. But you might have a diesel engines as emergency generator, so they could be running at a lot higher temperature because of the frequencies. So there's a lot of variances of the water condition needed. If you look at this, it's a simple drawing, but it's just to point out that over the whole engine side, which could be bigger than 10 meters high, The water system is a very, very small element of it. But the two main things we're looking for here is corrosion, either by scale corrosion or by metal deposit corrosion. It says here the engine systems normally contain multi-metal components. But you might have actually an engine with only aluminium, which causes itself as an important factor. So when we're talking corrosive metal cathodes, how the principle of making rust is basically moving the metal ions from one place to another, makes high corrosion levels. It is important that we get the water conditioned. And actually, going back to the boiler side, where I mentioned about that black or grey covering magnetite, this is what we're trying to do in the cooling water. But because we're working at so a lower temperature than the boiler, we've got to make the magnetite layer through other means and not just through the oxygen chemical. Otherwise, we get this. So basically, we've got the copper pipes attacking the galvanized pipes. But you've all done trading on galvanic corrosion, have you? Basically, what happens is the weaker the metal will be deposited on the least active correction on the most active metals. So it's basically depleting the metal from the softer metals. Another problem we find in cooling water is cavitation. This is something I don't normally talk about, but I've found this on more and more problems, especially on MAN engines. Cavitation is not something you can actually engineer out with chemicals. It's actually a problem designed by the manufacturers of the engines. But when we're looking at MAN system, they are having lots of cavitation in a certain location, just next to the fueling, next to the pistons. I'm going to say the fuel injector, but it's next to the pistons. And what they've decided is it's too expensive for them to engineer out the cavitation problem, where they've got a high velocity of water moving in such a small space. So they've actually decided, MAN, across the range to increase the nitrates in the engine water cooling chemical, double the chemical quantity, and that is actually putting the magnetite layer thicker where the cavitation is having a problem. So that they've engineered the problem out by putting more chemicals in there to stop the engine damage. So if you go on board a vessel with MAN engines, the recommendation for the nitrate should be 1,000 to 1,500. They're now saying 2,500 to 3,600 to get around the problem of the engineering mistake. Otherwise, you start getting pittings like this through cavitation. So the thicker the magnetite layer is giving the protection so the cavitation does not do damage. Normally, I would actually say you cannot engineer this out by chemicals because it is actually a physical movement of water. Other forms you should be looking at, we see it in engine waters more prominently, but it's actually in the boilers in greater numbers, but you don't see it until there's a problem, is fatigue cracking. And fatigue cracking is when you've normally overheated the pipe too long. And especially if you go in the heat stress for high temperatures and low temperatures and high temperatures, you can fatigue the metal, so you got cracking. And biological fouling. This is one of my biggest problems. Biological contamination. I said earlier on the boiler water, you should be using technical water at all times. You should also do that with the cooling water. But I can guarantee you most of you will be using shore water in your cooling water system, because a lot of vessels cannot produce enough water, technical water, for the boiler and the cooling water at the same time. The result is bacteria will come in through the shore water, which is not a problem for us to drink, but the nitrate depleting chemicals, that means nitrate depleting bacteria. And what that means is when they get into the cooling water system, they will start eating the nitrate, which is actually your protection for corrosion, and start blocking up your system, either by fouling, as in here, or they start making high corrosive areas, high corrosion and pitting. But one of the worst conditions is a combination of both, where they're using the slime to protect the bacteria, so the bacteria can do the pitting and the eating of the metal. And the worst case, it will take you a hell of a long time to clean the system. Killing the bacteria is one thing, but if it comes to this slime, if it gets slimed like it is here, then you've got something called a biofilm. And then you would have to use a very aggressive alkaline cleaner first, then a biocide to kill the bacteria. So it is actually what they have here is a very nasty, very bad situation. Cooling water treatments. One of the slides earlier was saying that we can have multiple metals in the cooling water system. That is generally not a problem. The problem is now we're having a lot of Scania engines, and what Scylla has now started bringing engines in, which are 100% aluminium. Aluminium does not get protected by normal nitrate chemicals. So then we have to have a choice. Do we go by an organic acid treatment, which is a cool treat AL or ALC, or do we protect it by another chemical called silicate, which is in Alfleet 2009-111. So depending on what metals in the engine system, we have to decide on some chemicals. Both of these choices are very good, but they both have a weakness. The organic liquid corrosion inhibitor, or we call it OATs, organic acid treatment, is long life. It would last up to 4 years without depleting, which is actually very good. That means you will you fill the engine up to start with, and it'll last for 4 to 5 years, which is very good if you've got no leakages. But if you've got a lot of leakages, the chemical is very expensive. So you're throwing away a lot of good chemical. So if you do an engine maintenance, you've got to make sure you've got an extra tank you can move the water over to make use of the long life of the chemical. The other side is if you go for the Alfleet 2000, which is a nitrate-based chemical, but it has silicate in it. It's cheaper, but you have to do more maintenance doses through the 4 to 5 years. So in general, they'll cost you more or less the same, but if you have leakages, the Nalfleet 2000 is a better choice, as in it's a lot cheaper to throw away. So these are decisions your chief engineers will have to make. Then we've got the non-aluminium systems, which are the most common systems. And our biggest seller is a Roco MB liquid, which is what I will be doing the training on next. But we have multiple different chemicals, again, for multiple different scenarios and different types of metals in it. And again, as the example was for the boiler, there's no consistencies with that same fleet. Again, a lot weren't actually doing what they should have been doing. But then we go back to the same questions. The only question different here is the boiler core, is the bacteria contamination? Because we've got the same problem. Where do we dose the chemical? How often do you do the testing? How often do you actually refresh a system? Because the engine manufacturers say you should be losing 10% of the water every month. So you got fresh water to bring fresh chemicals into the system. A lot of ships don't change the water over until they've got leaks. Then they're classed that as changing water. Here's some of the ranges we should be looking at on a general water system. A pH, neutral or alkaline, which is 6.5 to 8. Chlorides 50 to 100. But most engine systems don't want you to go above 50 ppm of chloride. I've put this here because if you're using shore water, and most probably some of the vessels you've used are using shore water, the chances are you'll never get your chloride below 50 ppm. If your shore water is 100 ppm, you will never get it below 100, because the chloride is a pollutant, natural pollutant, and there's no way getting that out of the system unless you replace it by better water, as in technical water. So then we go for the sulfites and the hardness. But your tests, how often should be doing the tests? Boiler, we say once a day. Cooling water, we say at least 3 times a week. And excuse me, when you're talking about the engine manufacturers, MAN and Wärtsilä now are recommending every 3 to 4 months you send a sample to a laboratory to test now, because they're now saying that they see too many problems with onboard testing. But our biggest chemical, Roco MB liquid. It covers the nitrate, pH, chlorides, and conductivity. And the dosing ratio is 13 litres per tonne. But one of our other products, we discontinued now because it's powder, and it was causing a lot of problems because people weren't mixing it, had a dosing ratio of 2 kilos per tonne. So there's a big difference in the quantities you use. And even though we've taken diesel guard out of our range, a lot of our customers are still asking for it, because one of the reasons we took it, one of the main reasons we took it from our range was if you didn't mix it properly, you would having lumps left in the bottom, sticky lumps. But a lot of customers, especially one I can particularly see, I've had meetings with in Norway, I had a long discussion with the technical management for about 4 hours because they wanted to keep this chemical on our range just for them. And every argument I could have with them why we needed to get rid of it for health and safety, damage to the systems, everything, they said, no, we want it. In the end, we said, let's go and have a coffee break. And one of the superintendents pulled me to one side and had a quiet conversation. And he said, the reason we want to keep it is because of everything you've said. I said, what? He said, you're telling me you don't mix it properly, so it's causing lumps. I said, yes, that's why it's doing damage. It's because it's high alkaline, it's causing the problem. He said, yeah, but see it another way. All my vessels have got leaking pipes, and these lumps are blocking my leaks up. So actually, it's solving their problem by blocking the leaks up, but causing other people problem because of the corrosion. He didn't actually admit that the lumps actually caused the corrosion in the first place, which was a possibility. But that is showing a difference in different attitudes of the personnel. So cooling water chemicals again. Another chemical is a very good seller from our range, Nalfleet 108. Bear in mind, the raw cranberry liquid is 13 litres per tonne of water. This one is a 2.25 litres per tonne of water. So it's very, very highly concentrated. And the reason is because this is designed for shore water. Raw cranberry liquid is designed for evaporated water. So this has got stronger chemicals in to combat the bad quality of shore water. Then the Nalfleet 2000, which has got a very high dosage rating of 32 litres per tonne, but it's designed for aluminium systems or small high-speed systems, as in your generators. Then if you've got a bacteria contamination, this is the chemical we have. It's called MAR71. That's the name of the biocide. And the active biocide, that's why we keep the name MAR71. It's one of the few chemicals which is allowed to sell in Europe for cooling water systems for bacteria. But it will only be good for bacteria which is open flow in the water. If it's been protected by biomass or biofilm, then this will not kill the bacteria which has got the slime covered on it. So that's why you need to do a full clean if you got biofilm. The last one, or nearly the last one, is a Cool Treat AL, which is what I've mentioned earlier, is an organic treatment. It lasts a long time, but it's expensive and it's high dosage ratio, 60 litres per tonne. All these chemicals can be mixed with glycol, with the exception of this one. It's already got glycol or antifreeze pre-mixed in it. So if you actually put a glycol in with it as an extra, it will reduce its corrosion protection. This is designed for high-speed systems, which you need a long life chemical because you don't want to test it that often, especially air-conditioned systems, where you might test once a year, and it's a very tight system. That's a glycol. I did mention earlier saying that MAN have chosen to increase the chemicals in their system so that the protection is. This is their service letter. And raw cranberry liquid mentioned earlier that MAN decided to increase the chemicals so that there's less damage to their system, one through cavitation and one through bad engineers doing the testing. This is an example. This is one of the service letters. The nitrate on Roco MB liquid is normally 1000 to 1500 ppm. Or that's a sodium nitrate, or nitrate NO2 is normally 1500 to 2400, which is the numbers here. But MAN have raised it now to make sure that no damage happens to their system. They wanted the extra protection. So they've now raised it from to 2,400 to 3,600, which is not a problem chemistry-wise. It just costs more to keep it up at that number. But I would just bring that to your attention, because when the pointer's gone again. See, that's where we recommend there should be 1,000. We recommend NL2 should be 1,000 to 2,400, compared to MAN's recommended 2,400 to 3,600. But in their service letter, they've mentioned number 3, failure to control inhibitors and the chlorine concentrate and pH levels. The coolant must be checked at least once a week, and every 2 to 6 months sending away to independent labs. The reason they've said that is because they've noticed a drop in engineers doing the correct testing and lying on the exact test reports. So, for reference, we have actually got a laboratory within Wilhelmsen which covers all the tests they're asking for, and here's an example of what they say. Compared to other laboratories, which tell you all what we're showing here, laboratories are generally just testing the water. But because our laboratory is part of Wilhelmsen Chemicals, we can actually give the customer, like it says on the corrective actions or comments. This particular one had a very high bacteria contamination. The nitrates was within the range of 1,000, between 1,000 and 2,400. It was 1,380. But the nitrite level was nearly double that, and nitrite NO3 is what's left after it's done its job. So there was a lot of old dead chemicals there, with bacteria in top of it, and the conductivity was 6,000 range, when most engine water is around about 2,000 range. So the water was actually very dirty and very full of bacteria. So they would have needed to replace the water and do a full clean. So like I say, we give corrective actions. Other chemicals which we class as in the cooling water system, and we class it as that, but a lot of people don't, is BioGuard or the seawater cooling system from your sea chest. A lot of the systems have electrical diodes, and others have chemicals. Our chemical is a BioGuard, which puts a film on your pipework, and it makes it taste horrible for the sea creatures. So they will just not settle and just go straight out the other side. And VapTreat is how you keep your evaporator clean of it cleans of all the salts and the brine, so it can do its job. Them are two important parts of the cooling water chain, which people forget about. As I was saying, through the seawater, that was actually in the wrong order, but that's not for so. This is where you inject the BioGuard into the sea chest. Now, the next section is waterproof. Waterproof is our software for logging all your test results. Has anybody used waterproof?
Yes.
Was it good or bad?
It's perfect if you don't have the knowledge. So it
It is,
says this is good or this is bad, and these are the consequences.
you've hit on the good side of it, yes. It is a very good program. It's showing its age now. It was designed, I think we launched in 2014. So it is showing its age now, but it's still the best on the market. As you mentioned, Max, it has actually got when you press enter, when you enter your results, it actually gives you corrective actions on the spot. So it's the only one on the market, and we give it free of charge with our chemicals. Only one on the market which actually gives you corrective actions. So it is good. We are hoping for the next generation to come out next year, but I'm not holding my breath. It's meant to be a lot more user friendly. So it is actually user friendly to an extent. It's still a software, and it is a little bit slow now. So when you type in your results here we've actually put in pH at 9.6. Pressed enter. It's saying the pH is too high. Reduce. This was obviously for the hot well. Yes, a hot well. It says reduce. Put in the condensate control into the system. This was a system which was using multiple chemicals. So when we go into the boiler water system, we can actually correction. This is another part of it. This is a cooling water. BW is a big shipping company in Norway. And here they wanted to change the nitrate values. So if you look down in the bottom right hand corner, they've got 18,000 or 1800 in blue. So when you actually type in a corrective into the custom limit, all your results after that date will be based on that custom limit. So like I was saying, the N want a particular limit. Some other engine manufacturers want different limits. Or the company you are working for might have its own personal limits. You can actually change our system from our recommendation to the custom recommendation, and all corrective action will be based on that new numbers you put in there. One thing I don't like about this program is too easy to make it simple. If you look on the top right, top left, the fourth one down, test frequency. Now, I prefer you to do the boiler water once a day and the engine water at least 3 times a week, because nitrate and other things can affect it within 24 hours. So if you do multiple times a week, it's good. But if you want to be lazy, you can actually change that frequency to 1. And if you only do it 1 time a week, you still the program won't tell on you. It will still say you're okay on for the frequency side. Because one thing that there's few parameters this program works on. One is a frequency. If you do not do it frequent enough, say you said once, if you said 3 times a week and you only do it 1 time a week, it will show up with the superintendent yellow. So he will know that you're not doing that often enough. Or if you are outside of the recommended limits, it will show up red. So it's a traffic light system for the superintendents. So you can actually engineer one of them problems, as in not frequent enough, by changing that to 1 on both the boiler and the cooling water. So that's a little cheat you shouldn't really be able to do. As on the traffic light system is here, is the yellows again. The test results are good, but they've not been done it frequently enough. The greens, everything is perfect, and the red, there's a problem. If I go into one of the vessels, this was actually yellow at the time. So green at the time, should I say. So this month, as you can see, if I go back into it, there's a yellow one, which is a service report. Then they've also got a green lab test. So that tells me that the lab test is actually all good. The service report was actually saying that that vessel hadn't done it frequently enough. But couple of months earlier, they had a lab test which was red. That means there was lots of problems. So when we go into it further, this is all what your superintendent can see. They can go further and see where the reds are, where the problems are. And if you look at the middle left column, the red one, with parameter conductivity, they can see your conductivity is dropped lower than the custom limits. And actually, that is actually good. That means that is for a boiler water system, which that means it would be bad. Conductivity is generally how much pollutants are in there. But if your conductivity is too low, that also means there's not enough chemical in there. So if the conductivity drops below 1,000, I know that they've been doing too many blowdowns and not put enough chemical in. So the custom limit there is a little bit too high because people think high conductivity is always bad. Low conductivity can also be bad. So they're trying to keep your conductivity on the high side. So that the systems need a bit tweaking. But like I said, this shows how easy it is for a superintendent to check on your scores. He sees your vessel as red or yellow. He goes into it, sees which ones he wants to look into, then sees which is bad. So now, do you like the program?
Yeah, I don't think we had a superintendent to begin with, so.
The facilities there for the superintendents. I've never met one superintendent who goes in there regularly. They normally see your reports, because if I go back to this, if I go back there, if you look on the right hand side, it says reports, resend. There's another tab passed on the other side of resend, and it says emails. And it actually tells you which email, when you actually install in the program, you can put as many email addresses as you want to receive answers from us. Most vessels put the superintendents and the chief engineer on there. So they will get a monthly reply back from us of how good you've been or how bad you've been. And that's what the superintendent normally looks at. They don't normally look into this program unless you've got a very bad report. Then he would like to check it a little bit more. But generally, they don't normally check on you. But the facility. Now we're going to the dosing of chemicals. We've gone through the chemistries and we've gone through the corrosive parts of the chemicals and the boiler systems. One of the important parts is actually how you dose the chemicals. And I'm sorry to say, majority of customers are still using the bucket or the measuring jug, which these are pictures that the middle picture is one I've taken of an engineer after I visited him on board a vessel. He went and threw chemicals into an open hot well, and he got steam burns as he's got there. So it is a very serious risk. Cooling water is not normally the problem, but well, actually, cooling water is a bigger problem because Depending on the chemical, you could actually have more caustic chemical. So actually, if you spill that chemical on you, you'll be doing more damage to yourself. Some cooling water systems you've got to climb a ladder to get to as well. So carrying a bucket or a jug up a ladder with caustic chemicals is not something I would prefer to do. One system we try and push a little bit better is a pump and bund system, which is a pump with a place to put the chemical drum so it sucks straight from there, like that. That means you don't have any chemical contact at all. So health and safety wise, it is a lot safer. You're not touching the chemicals, you're not getting chemical burns, and you can put the chemical into the location that is needed. That's a fairly low cost system with a lot better and put better chemistries for your systems and safer for you. So if you go on vessels where they're dosing with the bucket and the measuring jug, I would ask questions: is this safe enough? Am I complying with the health and safety regulations? Because you'll find out you're not on board the vessel. Changing a system like this could actually help the insurance of the vessel. So it's something to bring to the attention of the chief engineer. Chances are the chief engineer will tell you to piss off. It's too expensive. We're not doing it because the vessel's not with it. But at least you've tried your best. Because I've always said, health and safety is your responsibility before the vessel's responsibility. Even though the company you're working for has got to give you the safety mechanisms, and by law they're responsible, you are the only one who's going to get the damage. You're the only one who's going to have the pain. So you should actually take ownership of your safety before the company. So bring it to the attention, please. Same as other things like the sample coolers and stuff like that. If you don't bring it to the attention, it will never be improved. And if they don't improve it, at least you've tried. Well, actually, what you're saying could be correct. I've not got a picture here. It's a tank, normally a 60-litre tank, and you empty the container of chemicals, 60-litre sealed tank, and you pump from that.
Yeah.
Because a lot of vessels, that's an old system. That means you've got to lift a 20 to 30 kilo drum of chemical waist high to tip it in, which means that you're getting all the vapors from that chemical. For health and safety wise, it's not good for the vapors or the lifting. So what you'll find out now, most companies replacing the pump and tank to the pump and bund, which is a safer way of doing it. But until about 5 years ago, tank was very, very popular.
All right.
Okay. But you still didn't carry the chemical, it was just the lifting and the pouring which was the problem. And I've seen a Filipino trying to do it, and it's quite funny. When I think the chemical drum weighed the same weight he did. For me, I'm a big, chunky, fat person. I can lift it, but a Filipino, it didn't look right. So these are the positives why we do it in this way now. But another way is the more expensive ways, which is the better practices. One is flow proportional, and one is using electrical equipment to dose a chemical. So basically, it's getting the chemicals so that it's more refined and you are optimizing the chemical as best you possibly can without having any highs or lows. One of the products we have is AquaGuard boiler water system. It's using flow proportionate. to control the pumps for the chemicals. So this is the DMVs that have approved our systems, saying it engineers out a lot of the problems with the bad quality crew members. One, due to inconsistencies, just like you could be testing 1 week and you are testing your way, then your colleague will test the second week and he tests slightly differently. So you can have different results. And I'll explain that better on Thursday when we do the testing. But actually, eyesight can make a big difference. The way you actually shaking the tubes can be different. So this is more consistent and gives you better concern. So that's where DMV are mentioning all the. You've got copies of these, or you will have copies. So I'll let you read it. But they're really promoting engineering out the dosing. So flow proportional. On the left-hand side is a typical boiler system where you're using pump and bund or pump and tank, or once a day with a jug. So you are really seeing your engines, your boiler system running with X amount of steam. So if you're running at a standard pressure and you've got 5 ton of steam an hour, if you increase it when you need more steam to 10 ton an hour, say you're changing cargoes on a tanker or whatever reasons you need to change it, you're still only dosing the same amount of chemical, even though you dosed, even though there's more water, more steam, and the boiler needs more chemical, you're still only dosing the same amount. Maybe the dosing pump per hour or 1 jug of chemical per day. Proportionate, on the other hand, is if you're running at 5 ton an hour, it will give you what you need for 5 ton an hour. If you go to 10 ton an hour, the pump speed increases, so it doses the correct chemical for that amount of water being used. So you're actively dosing correctly. Because you're not actually physically testing certain parameters, the best word I can say is guesstimating. So it's giving you the best practice. After a couple of days of trial and error, you get to fine tune the pump to be able to work better. It's not perfect, but it's a good alternative to bad practices. So simple it is, you dose just before the feed pumps on the modulating valve. And what happens is when every time the modulating valve is opened, we mimic a 4 to 20 milliamp signal so that we control our equipment. We don't take any ampage from the modulating valve, we just mimic it. The cooling water system, on the other hand, let me go back to the boiler water. We do have the next generation, which actually we call it the full bells and whistles, is that we've got a unit which tests pH, conductivity, dissolved oxygen, and corrosion potential, and it doses the chemicals as per them tests 24 hours a day. So it's automatically testing and dosing individual chemicals. But that is in the price range of about $30,000 per boiler. So it jumps up quite expensive. Cooling water, on the other hand, this is what we call an active testing. On the top right hand picture, you'll see the pipework. From the left, it comes in, goes down, then goes horizontal again. Halfway through, underneath the screen, you'll see a wire attached to a probe. That's a conductivity probe. So the water will pass the probe, we'll see what the conductivity is, and a good cooling water conductivity is 2.5 to 3,000 microsiemens, which will give you 1,500 ppm of nitrate. So going back to the MAN letter, they would like you to do testing, and they've got problems with the concentration of the chemicals not being checked enough. Equipment like this will help a lot. So as I was saying, the water comes from the left down the pipe, so you've got an isolated valve straight away. You can actually turn the system off for maintenance. It goes down at the bottom. You've got a sample drain if you wanted to take a manual test per day or per week. Then it will go through a filter into the conductivity sensor. It detects if you need any more chemical. Then on the right hand side of the picture itself, you've got a white thing. That's where the chemical is injected. So the chemical injection is done in the same unit. So then you only need to actually do 2 pluggings, a half-inch BSP connection, one before the pump and one after the pump. And you use the positive flow of water to take the chemical back into the system. So here you've got a system which is one, health and safety good, because you only need to put the chemical drum in and put the suction leg into the drum. And 2, it's protecting the system by continually dosing chemical. And these are some pros of it. So it's dosing the chemical directly from the drum, so you don't have any contact with the chemical. It reduces the need for handling chemical by the jugs or the bucket, or lifting and pouring into the big bund or the tank. The bund is designed so if the drum leaks, it will contain all that chemical for safety reasons. Safe container and the health and safety. Does that sound logical?
Yes.
Perfect. Cleaning of water systems. Basically, there's 3 cleans. One, I would say, is a total clean. It's what we use commissioning cleaner. It is a slightly alkaline-based chemical which will take all the rust and oils out of the system. It's designed for when you commission a system or if you get a small contamination. Then if you get oil contamination in the system, we can do an in-service clean, so you can run it without stopping the engine for a period of time before you have to empty and flush and clean out properly, or an out of service using the same oil dispersant, C-Clean Plus. It's better to do it offline, but if you need to do it in service, you can do. If I were you, I'd look at the presentation on the PDF. Soot systems. I mentioned earlier about soot fires. We have an automatic dosing equipment for chemicals to be dosed into the exhaust manifold from your main engine, which will eat the soot away, or the chemical will actually assist in burning the soot, so there's nothing left to cause a fire before it builds up. And the combination of that and the chemical drum gives you an automatic system. It reduces any risk of any fires. It gives you control over it. And what it does is doses a little chemical 4 times a day, so that there's no build-up. These are just some positives of it. Even if you do it by manual means, it's still better than the possibility of a fire. But this is very easy, simple to use. and it's using air to push the chemicals around. This is going to be a shorter training, as it's only the testing and the test equipment. Here I'm going to be running through the presentation and some videos because we can't do hands-on training. Normally during this training session I will get you physically doing the water tests as you would do on board the vessel. Water testing. It's important for the water tests because there's only one way we can actually know what is in the water and if there's the chemicals or not, or if they're pollutants. So again, we've got multiple brands within Wilhelmsen. Unitor is for the fuel testing and the fuel chemicals with cleaners, and Nowfleet is our product range for the water treatment. So boiler water testing. We have multiple tests for different scenarios or different chemicals we're using. That's why I put them all in this one slide here. But in general, if you use the two chemicals we talked about the other day, which is Auto Treat and Oxygen Scavenger Plus, we have a set testing regime for that, which is a SpectraPack 315 with a DHA test kit, which is a 313. The test kit looks like that. It's for the alkalinity, pH, chloride, and condensate pH. Along with the DHA test, which is tested for DHA in this condensate water. DHA is a chemical which protects the system from the oxygen damage, but you test it for after it's protected the whole system, including your steam line. So you should only test DHA from your condensate sample line. We always recommend using conductivity meters and pH because if you're using pH paper, if you pull it out too quickly, it doesn't give you the correct result. On the other side is if you're using a pH meter and you don't calibrate it regularly, it again will not give you a good result. So you've got to use best practice on both ways of doing the pH. Now I'm just going to show you a video how to do the test for that. So as I stated when I started today, normally I would show the video, then have you all doing the test after me, or after the video. But today, as we can only use the videos, it's going to shorten the time down for the lecture. So please ask questions during the video or after the video so we can actually get as much information out of this as possible.
Excuse me, Christopher.
Yeah.
Don't think we can hear the audio.
That's what I was concerned about.
Yeah.
You should be able to hear it, but last time I tried to do this during a team meeting, I couldn't get it to work. So what I will do, I will talk over the video. I'm glad you clarified it for me.
Yeah, absolutely.
Because I can hear it loud in my ears.
Yeah.
Okay. So I'll start again. So basically, this is the 315 test kit, which is for the boiler water and the condensate water. As you mentioned in this slide, you have an extra one from 3112 or 313, which is for the oxygen scavenger, which I'll show you after this video. You should always use PPE. because some of these reagents can be poisonous. He is just repeating what I'm saying here. You should do the test regularly. Well, I'll let you read it. As we said, Connors, you should do it from sample cooler, and you should let the water sample run for a bit. Before we carry on, I will send a link to Matt's. In fact, I've given Matt's these last year, and I hope that he's still got them. All the videos, so you can have a copy of these videos. Then you can listen to it yourself. Okay?
Yep.
But on this, we will put in 200 ml of water sample into the jar. This is boiler water sample. Take one alkalinity test. When it dissolves, it should turn blue in color. But then we want it to change to a different color. And you add tablets one at a time until you have a color change. Now I'm going to stop it here. He says, and it says there, until it changes to a permanent yellow color. It does change to a yellow color. But if your water sample is not clean, as in it's got dirty black bits, you will never get a clean yellow color. So that's why I said you are looking for a color change. Because a lot of the boilers out there are not as clean water as he's showing. So you want a reaction from to changing blue to a lighter color. If you can get it as clean as this, I will be very happy. Also, if you actually overdose some chemicals, as in your hydrazine, if you're using a chemical using hydrazine, it will actually change it yellow. Then, about 5 seconds later, it will turn it black. And that's when you've overdosed the hydrazine and it's contaminating the sample. So what they're saying here is the calculation. Each tablet is worth 20 ppm, but you take 10 ppm for the first tablet away. So he's put 8 tablets in, which is 20 times 8, take away the 150 ppm. Is that a good result for boiler water? Anyone, any idea?
Go back so I can look at the result again. Just a second there. No, I think that's terrible.
Why?
So I think I only put in ever 2 tablets at most to get the color change.
Actually, you should be looking between 100 to 300 ppm.
Oh.
In the cooling water, then you would do maximum 2, if you do it on the cooling water.
Yeah.
But in a boiler, we should be looking at 100 ppm of alkalinity. So this is alkalinity. This is to find out how much alkaline your water is, and to make sure that it's not aggressive to the metal surface. So then you should record it in the waterproof program we went through the other day. And it will give you results straight away saying good, bad, start again. Now this is doing the chloride test. 50 ml of water. One tablet will turn it brown. And you want to change it to a light color again. Correction. You first it changes color. You want it turned into a browny yellow. Then it turns into an orange. But again, if you look at the video, First time it turns is light colour. And if you've got more than 100 ppm, it'll take a few tablets to get to this stage. But look at this colour, then look at the tablet next colour. It doesn't actually change colour, it changes depth of colour. So it goes darker rather than changing into another colour. Again, if you've got dirty water, this can be a difficult trying to see the colour. You're looking for the depth more than the colour. So the first tablet is forgotten about. So 2 tablets is 20 ppm times 2. Take away 1 tablet means you got 20 ppm. Always use 4 tablets there. Okay. The cooling water, you don't want more than 50 ppm. Boiler, you can actually boiler water. We would recommend not going higher than 100 ppm, but engine manufacturers will accept up to 300 if you are using shore water. Because shore water, chloride is a pollutant and you can't get it out of the shore water. So in this pH test, we are putting a salt into the water. The salt is only there to increase the speed of the test. It doesn't give you a more accurate reading or change the pH at all. It just means that the result will be quicker. He's using 6.5 to 10, so he's actually testing the condensate sample here because you expect a lower pH. So that result is round about, I would say round about 8, which will be good for a pH in the condensate. Here we'd expect around about 10 for the boiler. Now, if you didn't read what he was saying, he was said pay attention to the test results because a lot of your AMs recommend certain limits, which may be not the same as our limits. Here is the one for the oxygen scavenger, which again, like I said, this is our most common one, which is DHA. If you think you're going to be working with another oxygen scavenger, tell me and I can show the video on that one as well. So I'm going to start again a little bit. As I said earlier, this test has got to be taken on the condensate water. What I notice here is not giving you a good idea. When you are taking from the condensate water, notice is using a smaller bottle. Is using the smaller bottle, so he takes a smaller sample, lets it overflow with water, then puts a stopper on. With this test, you cannot allow any oxygen in that glass bottle, because that will spoil the tests and give you a lower reading of the chemical, which will result in you having to put too much chemical in the boiler. So you pour 10 ml into a glass cell. The point of moving it into this glass bottle, the secondary, if you're using high pressure boilers, yes, put it into the brown bottle. Because you need it a lot more precise than what we are doing for the general boilers. So you put it in the glass bottle, it'll be a lot more precise, but if you're using it on a 8 to 16 bar boiler, you do not need this bottle. It's just to make it sit for 10 minutes without any ultraviolet light being present. So if you're not using a brown bottle, you can put this straight into the cell. So you put in 6 drops of reagent plus a tablet. Then we'll leave it for 10 minutes. Like I say, a lot of ships lose that brown bottle, so you can actually do it directly into the cell. The second cell, you're filling up with the same 10 ml of water, but only putting the tablet in here. So now you've got 2 comparators, one with 6 drops and one with 6 drops and a tablet, and one with just a tablet. Notice the color difference. One should be clear with the tablet, and the one with the drops should have a color indicator, normally pink. Then you use your eyesight to see against a nice white light which is the closest match to that color. Everybody's eyesight is different, so this could be a slight problem, as in if I was doing a test and you did a test, we might have a slightly different color, but the results will be okay. Say, if you're not using high pressure boilers, you do not need to use the brown bottle.
But do you only take the test in the condensate water, or do you take the test from the boiler as well?
On the boiler testing, you'll use this test kit, the 315.
Yeah.
So you'll be doing the alkalinity, pH, and chloride. Then you'll take a condensate sample and test for condensate pH and chloride and DHA. I would only recommend you using it on the boiler if you have possibly condensate contamination.
Yeah.
And I was asking that because there's a few ships and color line fleet, we are having trouble trying to find a clean condensate line, which will give us a good indication of the DHA. And on them vessels, we do test it from the boiler. You can test it from the boiler, but the parameters are higher than what you would need on the condensate because that's unused chemical.
Yeah.
The one in the condensate sample is used chemical.
Yeah, have been in the steam system.
Correct. So we're looking for a smaller parameter, but we want a little bit of chemical left. That means the whole system's protected.
Yeah.
If you test it in the boiler, you are hoping the system's protected, because you cannot definitely say what is coming back in your steam.
Yeah.
But if you've got a good condensate sample which is giving you a good result before the hot well, then you do not need to do it in the boiler. If you can get it on the first chamber of the hot well, where there's no mixing of any water or chemical, that can be sufficient.
Yeah.
But you want to test one against the other for a couple of weeks to make sure it's good. But if possible, you get a sample directly from the condenser or just before it enters a hot well, that is the best sample. So on top of this test, or these tests, we actually have something called a spectrometer, or a lot of people call it a photometer. Most of the tests in the boiler can actually be done electronically now by using a photometer. As you can see, I've put a graph here which test can be used in which type of water: boiler water, condensate, cooling water, portable. You can test more or less everything except nitrate. So you could actually take away all these test kits and use the photometer. It's more accurate, it's a lot better, but it takes 3 times the length of time to do the tests. So you don't get anything without a payoff. And the vessels I know who have these on board have 2 or 3 of these on board, so they can quicken the test. So it can take up to 10 minutes for a DHAT, for an alkalinity test. Will take you 2 minutes doing it manually. So that's to be considered. Like I said, we do actually have another test kit. Have you anyone actually done liquid tests on the boiler?
Like water samples?
No, as in, I'll show you a video now. Let me just stop a second. Some years ago, we had 2 companies. One was called Unitor and one was called Nalfleet. And they were both very prominent in water treatment and chemicals, cleaning chemicals. But in 2000, I think Will Hubson bought Unitor, and that's why we've got Unitor brand in our range. Then in 2011, they bought Nalfleet. Because both of them two was working the same types of chemicals, we kept the brands, but we specialized one against the other. So we all the cleaning chemicals from Nalfleet we put into the Unitor brand, and all the boiler and cooling water treatment we moved into the Nalfleet brand. Nalfleet test was always liquid tests, and the Unitors was always tableted tests, which we've just seen. So we still have some chemicals you still need to do the liquid tests on. So I will show you the video now. If you say a Norwegian company like a Gearbulk or KG Jebsen's, BW still prefer the liquid test over the tablet. So there's still a lot of vessels using the liquid tests. I think it's better and simpler than tablets, but the shelf life of the reagent is a lot shorter. But I think it's more accurate. So as I was saying, liquid test comes in bottles, not the tablet bottles. We can do most of the tests we do with the tablets. Again, health and safety reasons, especially on the hydrazine, the liquid test is actually very, very poisonous. So again, we take a sample from a sample cooler or from the engine system, always trying to do the same point every time on the engine because you can get inconsistencies. So compared to the tablets, we're using a lot smaller sample of the boiler. You then put a chemical called MPA1 in it. It changes to pink. Then it goes to then you're trying to change a color to be a stable color correction. You're trying to clear the color as is there. So you put an MPA3 in there to actually neutralize the color. And you count the drops again. Each drop is worth 40 ppm. I'll repeat that because I was talking over it. So we're going to take a 20 ml sample of water instead of a 200 ml sample of water. Put 4 drops of MPA1 in it and it will turn pink. If it doesn't turn pink, you've got no chemical in the system. Then you add MPa3, which is an acid, and you're going to take away the color indicator. By the way, this is actually using the same technique as the CSIs check if it's human blood, not animal blood. So using Felling. So again, 120 is above 100, so it's still a good number. And you log it. That was a lot simpler test, a quicker test. Especially on the next one, instead of getting another water sample, we use the same water sample. And we call this conditioned water. We put in 4 drops of MPa1 in it. I'm going to go back a bit. Notice the angle on the bottle. That is actually on the limit. You should actually be using it up and down. Because if you actually got a bottle, say 90 degrees, the drop size is going to be 20% smaller. So if one person's doing drop sizes which are bigger than the next person doing smaller drops, the test results are going to be a lot different. So you should always have it as close to vertical as possible. We turn it to yellow, then we put another chemical, MBC2, to again go to a brown colour. But again, like I said, we are changing colours, not particular colour, because trying to get a pure colour is difficult if your water sample is not clean. If this is a boiler, is that a good result?
No, it's too low.
Yes and no. If you're using shore water, yes, it is too low. Because, say, Finnish, Swedish water, shore water is around about 100 ppm. If you get shore water, you can never get the chloride out. But if you're using technical water, that is actually on the high side. And for the cooling water, that is definitely on the high side because the engine manufacturers don't want higher than 50 ppm. But a lot of the ships working around Sweden and Norway are actually taking shore water rather than technical. So that's why it is low for you. The lower the better, though. You're allowed up to 300 ppm in a boiler system. So this is actually jumping over to the cooling water test, because the same liquid test kit, it's a combined test kit, so it does a boiler water and a cooling water. We might as well carry on to this cooling water because we will be doing this in about 5 minutes in the presentation. Here we're looking for sodium nitrite. On the liquid test, on the tablet test, we're looking for nitrate borate. But here we are putting 2 milliliters from the cooling water into the sample, put 4 drops of MN1 reagent, then we'll use MN2 reagent. We're going to change to a color of blue, but it's going to be a permanent color for up to 1 minute. So it can change to blue, you put it down, and if it changed to clear quickly, then you've got to put another drop to make sure it's permanently staying there for 1 minute. Now this calculation, if we're using sodium nitrate, we have a range between 1000 ppm to 1500 ppm. But because you've most probably all been using tablets, we're looking for nitrate borate in the chemical. Then we have to look for a range of 1500 to 3000 ppm. The end result is the same protection, but we're looking for different trace elements in the chemical. So if you've done the old tablet test in the past, this would actually tell you that it's too low, that result. I always said this man looks strange. So the liquid tests are different. It's a different way of getting the same results. The liquids are quicker to do the tests. To me, they're more accurate if you're using the bottles correctly. But the reagents, you will have to, basically you've got 6 to 12 months shelf life or working life of the reagents. So you can't order multiple test kits or refill packs. Compared to the tablets, you've got 3 to 4 years of shelf life, but they can be harder to mix, especially if your water sample is not warm. So going into the cooling water tests, we have multiple test parameters we can be looking at. As I mentioned in the liquid tests, we're looking for sodium nitrate, which protects most cooling water systems. But then we also looking for, in the Nalfleet range, or correction, the tablet range, we are looking for sodium, should I say nitrate borate, which is part of the sodium range, but it's looking for the borate trace elements. So you're still protecting the same type of system. If you're looking for like the Nalfleet 2000 we mentioned the other day, you're still looking for sodium nitrate, but you're actually using the protection of silicate. So it's sodium silicate, which is actually protecting your aluminium system. But you are looking for the concentration of nitrate to tell you how much silicate is in there. Then we have the other chemicals called Cool Treat, AL, which is organic elements, which protects all of the systems, but it's a long life chemical, which is very, very expensive. So as I said, we have different tests. So ROCM-B liquid, which is common for you lot most probably, will do the tablet test, which is a 3 or 9. And another chemical called from the old Nalfleet range is EWT 9108, which a lot of Norwegian customers prefer. That's using a liquid tests. So then we go into the tests. I end up having to repeat myself because there's different ways of actually explaining this. The test kit for the ROCM-B liquid and the diesel guard, which we've actually discontinued 5 years ago, but a lot of customers have still got lots of stock. So the test procedure is you're looking for nitrate, the nitrate boride, pH and chloride. The test range is between 700 to 2,500 nitrate, but the pass rate, you should be up to 1,500. The Cool Treat chemical, we use a Cool Treat AL test kit, and we are looking for a percentage of chemicals in water. So the test will actually give you a test to see if it's between 6 and 8% of chemicals in the water. Then pH and chloride again. Then the liquid test for the chemicals Nalfleet 2000, or previous name was Nalcure 2000. Chemical called engine water treatment 9108, which I said the Norwegians do like. And an old chemical was Nalfleet 911. Actually, I've written that wrong. It should be 911, not 111. And that was a very for 100% aluminium systems, but it was very, very susceptible to pH changes. So we've discontinued that one as well. We are looking for pH in the range of 8.3 to 10. And in this particular case, we actually use the P alkalinity to test on both cooling water and boiler water, because the chemical 9108 is actually a stronger chemical than the standard chemical Rocco MB liquid. So we don't want to put too much alkalinity in the system of the cooling water. So we actually say cooling water alkalinity is 40 ppm and the boiler water is 100 ppm plus. And in all cases, we would try and maintain a chloride lower than 50 ppm. But if, as I said, shore water, you were going to be really struggling to keep it below that. On the top of that, we have other chemicals, which is not part of the portfolio of this training. It was prominently for boiler water and cooling water. But to me, when you're talking about water treatment on board a vessel, you should be talking about all the waters, which is potable water, sewage and ballast. So I'll go through for about 10 minutes talking about them as well. So potable water, it is a very hot subject at the moment. A lot of vessels are actually being fined for the cooling water standard. In 2015, IMO, or the World Health Organization, brought it mandatory for vessels to do testing for the ballast water. And it became a law that if the vessel was not compliant and somebody actually died of bacteria in the water, the captain and the owner could be looking at prison sentences. So that is why it is a very hot topic. Even today, 5 years later, there's still a lot of companies are still trying to implement it. They're still trying to get ways around it. Potable water is any water which touches your body other than rain or sea. So that is including shower water, drinking water, ice cubes, even high pressure cleaning with water is part of the potable water table and could be susceptible to tests by the port stay people. So we have a basic test kit which comes with a incubator, which is like a bucket, a digital incubator, which means you can set. On top of that, with most flag states, you will need to add total bacteria, pH and chlorine, conductivity, colour and turbidity, Legionella, intestinal enterococci, and copper. Depending on the flag state, the IMO says your flag state says which tests your vessel has to comply to. But on most cases, these are the common ones. Test we can use a photometer with. To be able to comply to these tests, as in the bacterial tests especially, we have multiple chemicals. To kill the bacteria, you should be using a sodium or calcium hypochloride. And this is where the Scandinavian companies really do not like this regulation, because in Scandinavia, I live in Denmark, they don't put anything in the drinking water. They use natural processes, same as Norway and Sweden. But in the UK, they always chlorinate the water because the water in the pipes are so bad. So now the Norwegians, Swedes and Danes have got to get used to tasting or knowing there's chlorine already in the water. And a lot of chief engineers do not like to use that. Realistically, you should be testing the chlorine with the test equipment and having a very small trace of chlorine, 0.2 ppm. And that is enough to say there's no bacteria in there because there's a little bit of chlorine left, but it's so low you cannot taste it or smell it. If you can smell chlorine in your drinking water, the engineer department have actually put too much in. So then you can actually use something called a dechlorine agent, which is a bisulfite or hydrochloric acid. If you, as in sodium hypochlorite and calcium hypochlorite, they've actually got a very small window where the chemical is actually productively best. And it's between a range of 7.5 to 9 pH. So in certain cases, depending on shore water or if you're processing your own water, you might have to increase or decrease the pH to allow the sodium calcium hypochlorite to produce chlorine and within a kill parameter. On top of that, you might actually be on a ship with very old pipes. Old pipes mean all the protection in the pipes have gone, so you will actually possibly have red water coming out to your taps. I went onto an Indian-owned vessel 3 or 4 years ago, and every one of the Indian crew, bear in mind Indians are normally black-haired, every one of them was red-head. They had so much red water coming out of the taps that it actually dyed the hair red colour permanently. So in that case, we can put one of the two chemicals, potable water stabilizer, into there, which will stop the red colour from the pipes entering the water. And it's drinkable grade, safe to be drank. Ballast water is a new regulation. The regulation is that you are not allowed to transport species from one location to another. Water, just to highlight it, is water which you take into ballast a ship, even going from Gothenburg to, say, Fredericia, which is a couple of hours drive. You still, if you change your water, you've got to come under these regulations. The regulations are, in 2025, you've got to actually make sure that there's zero transfer of species. So the ways of testing it, we have the potable water test kit and what we call a ballast check, which is testing for live species. But the regulations is that you don't have to test for it, you just got to comply to it. So as long as you've got a ballast water treatment plant working correctly, they'll be happy. But we do have test equipment if you need to. And the sewage water, this came in 2 years ago. You all know that you put bacteria into your sewage treatment plant to eat the shit. But when you're finished with the process of sewage treatment plant, you've got to kill all the bacteria before discharge to sea. So the regulations are you now got to test for chlorine, pH, turbidity, and I think one bacteria. Correct. It's E. coli. So we have test procedure for that, and we have chemicals which actually allow you to do that. We have a test for the bacteria, which is permanganate, which is looking for oxygen demand of the bacteria and the chemical oxygen demands. And just a couple of other subjects while we're talking about chemicals. A lot of companies don't consider your safety. We put on, and we are the only ones in the world who have actually done this, every one of the chemical drums has got a safety data sheet underneath the sticker. Has anybody ever noticed that? If you lift the bottom right hand corner from the sticker, you'll see a user's guide for that chemical and with safety data in, I think it's 4 languages. And it's always up to date to the last batch manufactured. So the one on your label will be up to date to the manufacturing of that chemical. So if you ever ever need any SDSs and they tell you that you're not complying, just pull one of them little booklets off and say, that's this chemical, and do it for every chemical. You'll comply to that regulation. And also in our drums, we're trying to make it easier and better. We've put an indicator line so you know how much chemical is in there. We've also got ridges to make sure it stacks better. And one of the big things is a vent on the back, which allows you to pour it without splashing. It does make a big difference. We also got other oil tests, which is not part. Ooh, I've got these in the wrong order. Actually, I've got it in the right order. It's me going mad. I've added something on the oil test which I don't normally do, because you're most probably updated with the fuel regulation of 2020 for the sulfur. That's it. I lost the name then. For the sulfur tests, sulfur in the fuel oil now has been changed, and it came in January 2020. As a result of lowering the fuel oils, sulfur tests or sulfur in the fuel oil, in the diesel, we've seen a big spike in bacteria. So we're recommending now, if you feel you've got bacteria in your diesel, you should test straight away. Because if you do not test, it's going to block your system up and cause vessels blackout. I've done 2 vessel visits in Aarhus this year where they've had blackouts coming from France to Denmark because of all diesel they had on the tank, which has caused blockage in the fuel filters. So an easy test would be water in oil, where the bacteria normally live in the water cycle. So when you've got your diesel tank especially, reduce as much water as possible. It's a good way. You put it in the dark sample glass.
Yeah.
That is a proper way. And that's what my bosses want everyone to do. I personally don't think it's a good way, because on a low pressure boiler, I've done thousands of these tests. And a low pressure boiler, I'm saying low pressure, less than 16 bar. I've not seen any difference between putting it in a brown bottle than doing it in just a sample glass. If you've got above 16 and above bar boiler, it does make a difference.
All right.
It actually makes a big difference. For the main reason is you are looking for smaller percentages in the water, so you've got to be more accurate. Because on a high pressure boiler, let's talk about 32 bar and higher, normally we're looking at 20 ppm per tablet. the parameters on a 32 bar boiler, you are looking at 2 ppm per tablet. And more than 5 ppm of chloride, you shut the system down because it could explode. So the test parameters are a lot tighter. So then you would definitely need to have DHA in the burn bottle.
Very
So,
good.
so that's my opinion. Officially, we should always use a burn bottle, but one reason I don't like to use a burn bottle, and I've argued this with many chemists, and there's pros and cons to it each way. But when you're looking for oxygen, chemical which eats oxygen, which is DHA, every time you transfer the liquid from one jar to another, you are adding extra oxygen into that water. So even though pouring it into the burn bottle will take away the ultraviolet light, which makes it more accurate, you are actually reducing the chemical in that water to do its job. So you actually put in an extra parameter into that, which is not needed. And the chemists I spoke to, some agree, some disagree. But in the end result is, I don't see a difference. On your ship, if you had a pH meter or sensor, would anybody take responsibility in calibrating it?
No.
Then I would go for strips.
Yeah, that's what I ended up doing too.
Yeah. If somebody takes responsibility of keeping it clean and calibrated once a month and keeping the head wet, which you have to keep the sensor head wet, then I would 100% say, without even a question, pH meters are a lot better. But if it's just going to be thrown in a drawer and ignored between tests, then the pH strip are more accurate. It's only as accurate as long as you leave it in the water until it changes color. I always say, and this is because if you put it in the water, the strip into the sample water, and the water is not above 20 degrees, it's going to take longer for the color to change. So you actually could be reading a pH of 9 when it's actually 10.5 or 11.
Yeah.
So you've got to leave it in there long enough to finish. But if you take the strip out and leave it on the desk for 10 minutes, the color will start going back to the original color. So if you take it out, don't record the numbers, then look at it 10 minutes later, that number would have changed because it would have got drier and changed into its neutral color again. So it will never go past its original, it will never go past the water pH. If you leave it in there 1 hour, it will stop at its number and will not go past it. But if you take it out, it can actually give you the incorrect number within 2 minutes. So it's important that if you take it out, make sure it's finished changing. And when you take it out, record the number then, not 5 or 10 minutes later. You can also do chemical tests for pH, but I wasn't going to confuse you with that one. And that is actually a more accurate way of doing it if you've got clean water. But we're not going to show you that today.